So this is 6.4 part 1. We're just going to talk about the gamma function in this video. So the gamma function is defined, here's the symbol, it's the gamma of x is the integral from 0 to infinity, t to the power of x minus 1, e to the minus t, and that's a function of t. So let's start writing out some of these. Let's first find gamma of 1. So plugging in 1 for x, you can see there. So that's t to the 0, which just makes that go away actually. So since it's an infinite integral, we use the definition. The limit, we use b goes to infinity. So we get minus e to the minus infinity 0 plus 1. Let's find the next one. It looks like we're going to have to use parts on this one. Remember the formula for this is integral u dv equals uv minus integral v du. Now also, if you notice, this and this are identical, and that's just the definition of gamma of 1. But we still do need to work out. So we're just taking the limit. The limit is b goes to infinity of minus b all over e to the b. It's the first term. The second term is going to be 0 because we're going to be plugging 0 in there. And it looks like that. We can apply L'Hopital's. That's the limit. B goes to infinity. 1 over e to the b, which is 0. So this is still gamma of 1, which is 1. T squared. We'll do parts. Okay, so let's write it out. And I'm going to skip writing the limit. I'm just going to write 0 to infinity. Then minus, which is actually plus. So, again, not looking at the 2, but looking at the t e to the t, that's gamma 2. This is gamma 2. Now, this is still going to be 0. Because just think L'Hopital's twice. You'll get 1 over e to the t, and then when you plug in 0, you get 0. So this is still 0. So this is going to be 2 of 2, which does equal to 2. So this becomes so can we see that again this goes to 0 and this becomes gamma of 3. It's right here. And I guess we did have here, that was gamma of 1. So do you guys see a pattern here? Gamma of n plus 1, 1 less, n times gamma of n. And what is it? 3, 2, 1, 3 factorial, 2, 1, 2 factorial, 1 factorial, and 0 factorial, which is 1, defined to be 1. So that pattern works to be n factorial. So in general, this works for x also. Okay, so let's evaluate a few gamma values. Let's go ahead and try to find gamma of 5. Just using the formula 4 factorial, which is 4 times 3 times 2 times 1, which is 24. But what if we want to find gamma 4.5? So what if we want to find gamma of 4.5? Well, we can't take 3.5 factorial, so we got to use the formula. So how are we going to do this? Well, let's maybe change this to a series. Remember the series of e to the t, k equals 0 to infinity. Well, then we can just replace that t with a negative t. So e to the minus t. If we want to write a few of them out, 1, 0 factorial, 0 power, it's 1. And then for k equals 1, it's minus to the 1 factorial, plus t squared, 2 factorial, minus t to the third. So we could just replace it. Distribute. Just adding one more to it, 5.5. But of course, this would require plugging in b, taking the limit, a little bit of work. I mean, we can do it for the first t to the 4.5 divided by 4.5. And there's the hard part. So another way of calculating it. Sometimes your book will have a table of values too. I actually can do this here. So you can see you just type in gamma function of 4.5 and you hit enter. And this is what comes up. The input, the output. So it's about 11.6317. And we can see it's also 3.5 factorial, which we already derived, and some other interesting things about it. So there you go, 11.6317. So we're going to actually find once we find this, we can use this to find other values, okay? So I like to find this because it uses a lot of calculus that you haven't seen in a while, probably. Maybe some Calc 3 techniques. So we start off by using the definition. So it's t to the half minus 1, which is minus 1/2. So the substitution we're going to use, we're going to let u equal to, actually, we're actually going to go backwards here. T equal to u squared, dt equal to, instead of using square root, 2u du. And this will cancel that half power, which is what we want. And also, we're going to need this picture. We've got u, and this will be v. You'll see the use of that in a minute. So let's go ahead and do that substitution. Okay, so plugging this in. So we get u squared to the minus 1/2, e to the minus u squared, and dt just gets replaced with 2u du. Power to power is minus 1. And we can see that does cancel with that. And we'll hold off on those. Well, actually 0 still works and infinity still works. Okay, just thinking about that, plugging it in. So it looks like this becomes 0 to infinity, e to the minus u squared. We'll put that 2 in the front. Du. So maybe that's not an easier integral. But I have a trick up my sleeve. We're going to calculate. So we're going to calculate this twice. Remember, that is that. Okay? And so we'll call one of them, one of the integrals of a half, will just be that. That's one of them. And then I'm going to do another one. But instead of u, I'm going to just change out the variable to v. Okay, so what we have here, This is tau of half. This is tau of half. And let's simplify it. This is equal to 4. Okay, and we can bring these integrals together. And like I said, up here, this will be v, and this will be like my r, kind of like an x, y, and r. So 0 to infinity, 0 to infinity. I add these together, and it's minus v squared plus v squared du dv. Okay. Well, we see where we're going with it. I already kind of give us a hint. We're going to change that to r. V squared plus v squared equals r squared. We can also utilize, if we need to, u equals r cosine of theta, v equals r sine of theta. Polar coordinates. Okay, we're going to work on this inside first. So we'll do r d theta, no, I'm sorry, r dr on the inside, d theta on the outside. Okay, so theta's on the outside. Looks like we're going to do 0 to pi over 2. And r is in the inside. We'll have the same limits. My function is e to the minus, that is r squared. So this little blue thing right here, we're going to work on the blue right here. Okay, hopefully we can fit it in there. Okay, so we're going to do a substitution because it looks like just a simple u sub will work here. U equal to, well, might as well bring that negative in there with this. And then minus 1/2. Get right in the front. From here, the r will cancel. 0 still stays 0. Infinity. Still infinity. And integrate this. But before we plug in, we do need to go back. So minus 1/2. We're really taking the limit as b goes to infinity of e to the minus b squared. And then minus e to the 0. Let me plug that in. Minus 1. So this one's 0. And then I get minus a minus 1/2. Positive 1/2. Okay? So again, this gets replaced with this. So let's come down here. That's equal to 4, 0 to pi over 2 to the 1/2 d theta is 2 theta from 0 to pi over 2, which is 2 times pi over 2 minus 0, which is pi. Okay, that's not my answer. Remember, that whole string was gamma of 1/2 quantity squared. We had 2 of them. Therefore, and definitely something you want to memorize so we don't have to calculate that every time. Okie-doke. Let's do a couple problems now. Okay, so gamma of minus 1/2. Well, if we subtract 1 from it, that's minus 3/2 gamma of minus 3/2, and that does not get us very far, okay? Why don't we try gamma 1/2? If I subtract 1, it's 1/2 minus 1 is minus 1/2. Gamma of minus 1/2, and that's what we're looking for, right? And we know this is the square root of pi. So we call this square root of pi. So now we have an equation to solve. We basically have this equation to solve. So I clear my fraction. Gamma of minus 1/2 is minus 2 square root of pi. Pretty simple, huh? Let's do another one. Well, remember our oopsies earlier? It's sitting right in front of us. So that's what we really want to start off with. We just found gamma negative 1/2. And we know if we subtract 1 from minus 1/2, it's minus 3/2. So let's start that way. Gamma of minus 1/2 is minus 1 minus 1/2. It's minus 1/2 minus 1, which is minus 3/2 times gamma minus 3/2. And we just found this is equal to minus 2 square root of pi. So we just multiply by negative 2/3. And we get our answer. Pretty cool, huh?